Let's understand one very important term when it comes to graphical method of solving LPP: binding constraints. Binding constant is an equation in linear programming that satisfies the optimal solution through its value. Finding the satisfactory optimal solution through the certain value by using the equation in linear programming is known as a binding constant. In simple language, a binding constant is one whose value will satisfy all the constants. Let's assume point x is where our objective function is optimized. If we put the value of this point in any constant equation, we should get left hand side equivalent to right hand side. Then the corresponding constant is known as binding. Otherwise, the constant will be called non-binding. Let's take the same example as the previous numerical. Here, the optimized solution was found at point C, whose coordinates were 1000, 500. This we have found by solving the problem. When we put the value of this point C in all the three constants, we will know which is binding and which is not. So for the first equation, that was x1 plus 2x2 less than or equal to 2000, let's put the value of point C here. So putting x1 is equal to 1000 and x2 is equal to 500, we find that LHS is equal to RHS. That means this particular constant is binding. Similarly, putting x1 is equal to 1000 and x2 is equal to 500 in second constant equation, that is x1 plus x2 less than or equal to 1500, we again find that left hand side is equivalent to right hand side and hence it is also a binding constant. But putting the same in the third equation, that is x2 is less than or equals to 600, we find that LHS is not equals to RHS. That means this is a non-binding constant. And if you again look at the graph, the third line is not touching the point C, which is the optimized solution point. So you can also tell by looking at the graph that which constant or line is binding or non-binding. Now let's understand some special cases for graphical method. First is a unique solution. When the slope of objective function is not equals to slope of any of the constant equation, just like in the numerical we have solved, where slope of the objective function was minus 0.6, slope of first line was minus 0.5, for second and third line was minus 1 and 0. Here, the slope of objective function was not equivalent to the slope of first, second or third line, and hence this one had a unique solution. The second special case is a multiple optimum solution. That means more than one solution. When the slope of the objective function or m suffix z is equals to slope of any of the constant, then there is a chance that there is more than one optimum solution or multiple optimum solution, provided that two conditions are satisfied. Condition 1, constant whose slope is equal to the slope of objective function must be a binding one. Condition 2, constant whose slope is equal to the slope of objective function must be a non-redundant constant. The third special case is of a no solution. When there is no feasible region to be found, as you can see in the graph, the solution thus obtained would be regarded as a no solution. Next we have unbounded solution. When the greatest value lies at infinity in the problem, as you can see in the graph here, the solution would be called as a unbounded solution.